Hello.
Hi.
Let's see here. There we go. I don't have any students here in North Platte yet, as you can see. But hopefully they'll start showing up soon. All right. Well, let's. So we are in chapter 5 now, I believe. Further applications of Newton's laws. And I put a lot of questions in this one, but I'm probably going to erase a few of them. And I haven't really decided which ones yet. But we'll get to that later. So anyway, chapter 5 is further applications of Newton's laws. And it is after this it's usually after this chapter that we have an exam. And I can't remember if I made an exam yet. I don't think I did. No, I did not. But we will have an exam very soon here. Probably I will make the exam today or tomorrow, and it will be open until sometime beginning of next week, so that you can finish up your homework and take some time to schedule an exam. Usually my exams are designed to take about an hour and a half, and I'll usually give students 2 to 3 hours to finish them if they want. And you will take them with a proctor, which means you need to have a school or a library so that you take the exam out. You can do it at one of the extension campuses, or at the other campuses, or you can do it at a school or library. And I will send the password to a teacher there or a librarian there, and then you can hello. And then once I have sent that to them, you can set up an appointment and take that exam.
I hope that wasn't too vague of an answer.
Nope.
Okay, we started the class already, guys. So that is that. So just to recap just a little bit, after chapter 5, we'll have an exam on the first 5 chapters, and it's an exam that you will take with a proctor, which means you can take it at the Success Center here on campus, or you can take it with a teacher on another campus or a librarian. And you need to tell me where you're going to take that, and I will get the passwords to that person. The exam will probably be due sometime in the beginning of next week. I haven't made the exam yet, but when I make the exam, I'll put the due date on it. And it'll just kind of be up to you to choose when you take that exam and to set up that appointment and then to take the exam. The exam is open book. It will not be open notes, but it is open book. You can use your book online to take that test if you want. Just tell your proctor that you're opening. I generally tell my students to open 2 windows, one with the test in it, one with the book in it, and then you can just go back and forth between those windows. But please don't open up any other windows on the computer, because proctors will check for that.
Mr. Daly,
Yes,
this is Success Center over
yes, it is. It is just around the corner from the bookstore. Okay, so now we are into chapter 5, further applications of Newton's laws. They have this great picture of a hip replacement made of stainless steel or titanium or something. And the reason that they put that in there is because right at the joint here, this piece right here and the piece that's outlined up here are both made of a plastic type compound for low friction. And friction is one of the things that we'll be talking about quite a bit in this chapter. We've already talked about it in a very basic ways. We talked about the force of friction opposes relative motion between systems that are in contact with each other, surfaces or whatever. And we have a couple of different kinds of friction we're going to talk about. We're going to talk about one that is called kinetic friction, one that is called static friction. And just from those 2 words, can you figure out the difference between them? Kinetic and static friction?
Wouldn't kinetic friction be friction as fluid?
Okay. Kinetic friction is friction between moving things and packer.
Static friction is friction between still objects.
That's right. So static friction would be friction between objects that are sitting still. Why the difference? Why do we say that there's a difference? Why do we make them different? What do you think, Tyler?
Because if there's friction between 2 objects that aren't moving, there's a possibility of holding in place.
Okay. So static friction holds things in place, whereas kinetic friction just opposes the motion, kind of thing. Okay, that's close to what we're talking about, pretty close. Have any of you ever tried to move something that's held in place by friction?
Yeah.
Have you ever noticed that once you get it moving, it's easier to keep moving?
Mm-hmm.
This often happens with things. Once you get something moving that has a lot of friction opposing its movement, you don't really want to stop it moving because you know that it's going to take more effort or more force to overcome that initial static to get it going than it does to keep it going. And that's the reason. The real reason is because static friction is actually greater than kinetic friction. For some reason, when things are sitting still, they have more friction between them than when they actually get moving. And here is the reason, actually. It is actually a microscopic thing. Microscopically, all surfaces, even smooth surfaces, have bumps on them. A great way to illustrate this is to go ahead and look at some pictures of smooth surfaces. So let's go to our Google and let's look up the scanning electron microscope image of glass. So smooth glass, if you look at it really up close, what's your question? Oh, yes. So thank you. I always forget to turn on the screen. So here is a classic image, hopefully coming up here soon. Here's a classic image of smooth glass as it is imaged by a scanning electron microscope. Now, scanning electron microscope does not make a visual image of things. It scans the surface of things using electrons, and then it gives a computer-generated image or a either computer-generated or a refractory-generated image. So this is not actually a visual image of it, but it is pretty close. And you can see here that this surface is not smooth by any means. There's dips and bumps and holes and all kinds of things. If you look even closer at it, you'll find that it's actually even sharper or even more there's even more stuff going on down here. This is actually gallium nitride. This is more glass. So there's, if you look even closer, you start to see crystalline structure, and it really starts to get quite bumpy. So there's no such thing as smooth. I mean, glass, which is pretty smooth and can be made pretty smooth, is not even very smooth up close. Let me see if I can find an even closer image of glass up close. Can't seem to find a closer one. But anyway, glass being quite smooth to the touch, quite smooth to our eyes, not all that smooth. And the friction happens when the non-smooth parts on, or those bumpy parts on both surfaces kind of lock up together. Now when that's at rest, those things tend to lock up a little bit deeper when it's not moving. They kind of settle in, find a good space to be comfortable, and then they're just locked in really tight. Once you get it moving, what happens is, one of the things that happens is you actually start to smooth out these surfaces a little bit. You start to get little peaks bumped off, you cut off little things and you scrape it a little bit flatter maybe. And also, as it starts to ride up and over the top of these things, it gains a little bit of, you could think of it as momentum, I suppose. You can just it kind of gets going, and so it doesn't have to overcome as much because it hasn't settled down inside those peaks and valleys and hasn't really locked itself in. But once you stop it again, it'll find a nice, comfortable place, and it doesn't take much for it to find a nice, comfortable place once you've stopped it, and it'll be hard to get it started again. But how do we determine how much friction there is? Well, this is one of the instances in physics where you really start to realize how much physics is just observed. In order for us to know how much friction there is between two objects, we have to know, first of all, what objects are made of. If one object is made of wood and one object is made of steel, then we go out and we measure how much frictional force there is between wood and steel. And how would you measure something like that? Well, if it's a box like this, we would push on it and push on it and push on it and push on it until it started moving. And once it got moving, we would measure how much force we had to push with to make it move. And that would be what we call the maximum static frictional force. The maximum static frictional force is this F sub S, static frictional force, and it has to be less than or equal to a static coefficient of friction, we're going to call it, and the normal force on the box. Because it turns out the weight of the box matters, or how much the box is pushing against the surface because of weight, or the normal force pushing back is more to the point. So, excuse me, if you know that normal force that is pushing these two surfaces together, and you know the static coefficient of friction between these two materials, then you can calculate the maximum. If you make this into an equal sign, you would calculate the maximum frictional static friction that you could get from those two materials in that situation, with that force holding them together. So the normal force in this case is kind of the holding together force, the force that's pushing these two surfaces together in some way or shape or form. It could be gravity that's pulling it together, but it could also be just something pushing it down, pushing it sideways into another object. But
So, could you still have friction in space?
oh, absolutely.
It would just be a lot easier to overcome these instead of trying to like slide stuff working awkward.
Depends what's causing the friction. Remember, there are two things that we use to calculate the friction, but only one of them causes the friction. The thing that causes the friction is the force that holds the objects together. So if I'm out in space and I hold my hands together, push my hands together, I can create friction just as much in space as I can on Earth, right? So that normal force would be the force that I'm pushing my hands together with. But this inequality tells you what the static frictional force will be up to a point, because up to a certain point you're going to give it so much force that the frictional static force won't be able to overcome it, won't be able to stop the thing from moving, and then it'll eventually move. So that's why it's as an inequality. The frictional static force is less than or equal to this value, the static coefficient of friction and the normal force. If you have any other force that is greater than this, then the static frictional force won't matter because it's going to start moving. There won't be any static frictional force. Now that can be a bit confusing, this inequality, but we'll show you how to use it in a little bit here. But what is this mu sub s? What is this coefficient of static friction? That's the thing we measure. When we want to know how much static there is between a box and a steel floor, we have to go out and measure how much force you can push on the thing with, and you discover that the heavier the box, the more the friction. That's because this normal force is part of it, right? And you have to go out and measure how much that mu sub s, or the friction, the coefficient of static friction is for every material that's out there. So if you come up with two materials that you're going to measure the friction that nobody's measured before, you're going to have to go out and measure it. Because all of them have to be measured for you to calculate that frictional static force. Here's the equation for that maximum that I told you about. You replace that inequality with an equal sign, and you will calculate the maximum amount of frictional static force that can exist in a particular situation.
Before it moves, right?
I'm sorry?
Before it moves, right?
That's correct, before it moves. That'll tell you how much friction the box can have until it moves. But then once it moves, we have to switch over to kinetic friction. And look at the equation, it's so much different. They replaced S with K. It's not all that different. But in kinetic friction, it doesn't matter how fast you're moving. As long as it's just surface against surface, the kinetic friction is going to remain fairly constant in most cases. So you can just use this all the time. You don't have to use a less than or equal to sign and think about it too much. But it's now a different coefficient of friction. And the coefficient of friction for the kinetic friction force is going to be a smaller number for the same two materials as the static coefficient of friction, because the kinetic friction is a smaller friction. And here we have some different coefficients of friction between different materials. Here's a static coefficient column and a kinetic coefficient column. Notice that rubber on dry concrete has about a 1.0 coefficient of friction for static coefficient of friction. There's a 0.7 coefficient of friction for kinetic friction. And you can see that rubber on wet concrete is less because, of course, you're going to slip and slide on wet concrete. So it should be less. It's 0.7 for static, 0.5 for kinetic. And things that you really don't want to be sticky, you don't really want to have a lot of friction. Teflon on steel, 0.04. That's the kind of plastic that they put in that hip joint at the beginning, that we saw at the beginning. And notice that it doesn't change kinetic to static very much. That's good because you don't want to have to push to get your hip moving, right? So you want a material that has a very low coefficient of friction for both. But bone, lubricated by the synovial fluid, which is what it's supposed to have in there, is much better, much lower.
And with steel on steel, when it's oil, would be like basically how an engine works.
Yeah, so steel on steel for kinetic friction is 0.04 and 0.02. Steel on that's steel on ice. Where's steel on steel? Oh, here we go. Steel on steel oil. 0.6. I was going to say 0.04 is kind of small. Let's see, where'd it go? Steel on steel, dry, 0.6. Not very good. It's about the same as metal on wood. It's about the same as rubber on wet concrete, wood on wood. And that's bad. However, if you oil it, you can cut it in half. If you oil it with a synthetic lubricant, which has Teflon in it, usually, or something similar to Teflon, then you can lower that by almost a factor of 10. So you get much better engine performance because you get much fewer things rubbing together and creating friction. Friction, of course, creates heat. Heat creates expansion of metals. Expansion of metals causes problems in your engine because it releases seals. It causes strains and stresses. Yes?
What exactly is Teflon? Like I've heard it. Word
Just an organic compound. It's a plastic. Something that if you take a chemistry class, which you will, you'll learn more about what Teflon is. But it's just a string of carbon atoms with a bunch of hydrogens and methyls and other things hanging onto it, like most plastics. In fact, synovial fluid is also the same kind of thing. It's actually also, they call these things, they call them, I can't remember the name for these long strings of carbons. Anyway, there's a name for them. And the synovial fluid is another one of those, another kind of that same stuff. Most of the things in our body that are designed to be slippery are kind of like plastics. They're just plastics that our body makes. Plastic, waxy things. Well, yeah, exactly. Whereas Teflon is a man-made one, but it's still the same chemical concept. So it's just a different one. Polymers, that's what they call them. So you've heard of polymers probably. Polymer just means many carbon strings, many carbon atoms all lined up in these long strings. So it's a polymer. And so is synovial fluid, also a polymer. They're both organic polymers because organic just means that their base is carbon. But just the Teflon is a synthesized polymer and synovial fluid is a natural polymer. All right, so anyway, let's do some examples. Skiers, 62 kilograms, sliding down a slope, coefficient of friction, if the friction is known to be 45 newtons. So we know that the frictional force is 45 newtons. We want to figure out what is the coefficient of friction between the wax on our skis and the snow on the slope. Right? So here's the drawing. We have our skier. Notice that the weight from the skier goes straight down. That's very important because we're on a slope. The weight does not go perpendicular to the slope, it goes straight down towards the earth. And that means we can split the weight into two components, a perpendicular component and a parallel component. So that when you add those two together by putting them head to tail, tail to head, you get that weight vector straight down. The frictional force, of course, will go backwards from the skier's direction because it opposes the direction of motion. So here is the skier's direction down to the left. The frictional force is upward to the right. And they've given us that frictional force, so now we're going to set up our free body diagram. We have the normal up, the force back, the weight down, the two components of the weight force here. And you can see from this diagram that the perpendicular weight component is going to have to cancel out the normal force upward component. They're going to have to be equal and opposite because the skier is not going in that direction, right? The skier is not going perpendicular to the slope, he's going parallel to the slope. That's his only movement. So if he's not going perpendicular to the slope, then those two forces have to add to be zero because the net force in that direction has to equal zero according to Newton's law.
So you're saying the weight that's perpendicular to the slope.
This weight component right here has to be equal and opposite to the normal force here.
But the weight that's parallel and then
This
total
weight
is
here,
gonna be more, which is causing forward motion.
that's right. So this part of the weight is the part that pushes the skier down the hill. This parallel component is pushing the skier parallel to the hill, and therefore that's the thing that creates the downward motion of the skier. And that's why when you have a steeper hill, you get more speed because you have more of your weight is in that parallel component, the steeper the hill. So it pulls you down further and faster and faster and faster. However, the frictional force is the other component that we need to deal with. So in each dimension, we're going to have an equation. The sum of the forces equals mass times acceleration. In the perpendicular direction, we're going to have the normal force plus the perpendicular weight force, and the perpendicular weight force will be negative, will have to equal zero. So in the end, it's going to be normal force minus weight perpendicular equals zero. We solve that and we get this equation right here. The normal force equals weight perpendicular. Then the perpendicular weight is just the weight of the skier times the cosine of 25 degrees. Notice up here that the 25-degree angle is next to our perpendicular weight. So that's the cosine side, right? So the weight of the skier times cosine 25 gives us the perpendicular weight of the skier, and that has to equal the normal force. Well, the normal force then is just equal to the weight of the skier times cosine of 25. And the weight of the skier is mass times gravity times cosine of 25 degrees. We're good to go. We just solved that for the normal force. And that's one of the things we need to know to calculate the friction, or the frictional coefficient in this case. We have to know the normal force. So let's put a little stamp on that and remember it for later. And then we go to our kinetic friction equation. The kinetic friction equation says the force of friction kinetically is equal to the kinetic coefficient of friction times the normal force, which in this case the normal force is mg cosine 25 degrees. Right? Because we already calculated the normal force. So if that's the case, we need to solve this by dividing by mg cosine 25 on both sides so we can calculate the coefficient of friction in u sub k. When we do that, this is the equation that we get over here. We plug in the force of, the friction from kinetic movement, 45.0 newtons that they gave us, divided by all this stuff that comes from the perpendicular direction for the normal force, and we get an answer of 0.082 for the kinetic coefficient of friction between skis and snow. Does that make sense? We go back to our chart up here. Skis on snow don't have a lot of friction, but they do have some. And we say that's pretty close to steel on steel oiled, maybe?
Wax wood on wet snow. There's an option for wax wood on wet snow.
I don't think they have one, do they?
It's at the very top.
Oh, there we go. I didn't even see it. Thank you. Waxed wood on wet snow. They're saying kinetic friction about 0.1. We got about 0.8. We can live with that. Of course, skis these days aren't really made out of wood, but we'll give it to them. All right. Here's an interesting diagram. This is a representation of the most powerful microscope on the planet. It is called a atomic force microscope. And all it really is this needle that is made up of atoms that have been deposited on top of each other. And notice that each one of these spheres represents an atom. And at the very tip of this needle, we have 1, 2, 3, 4, 5, 6 atoms. How sharp is the tip of this needle?
Very sharp.
Very sharp. And you ask, well, how can they possibly make it that sharp? It's very clever how they do it, actually. They use what's called a vapor deposition chamber. And they lay down a layer of atoms just by evaporating the atoms in the chamber. Everything in the chamber is hot, except for the thing that they want to deposit on is cold. And so you evaporate this hot atoms into the chamber, and hot atoms stick to cold objects. So it sticks to the object. But the object is configured in such a way, has shapes painted on it in such a way, that every subsequent layer that they lay on it gets smaller and smaller, kind of like a pyramid, kind of like a round cone. And they just keep doing that, and with that with evaporation, you can get single layers of atoms, and you can keep doing it until it gets extremely sharp, as long as the material is a material that you can do that with, like molybdenum or gold or something like this. A metal that's really quite, has a very nice, stable crystalline structure. And so they can make these tips very, very, very sharp. And then they take that tip and they run it really close to a surface that they want to make an image of. So this is some crystalline structure, maybe salt or something. It's obviously got two atoms in it, two different atoms. But as you bring this thing across this surface, it actually never touches the surface. Remember when we talked about the forces last time, the four fundamental forces? There's that electromagnetic force, which is the force that is touch. Well, when it's a very, very small group of atoms down here, that effect is multiplied quite dramatically. The electric field coming from the electrons on these atoms is extremely strong because of the small point. And so instead of it touching anything, it actually just glides over those, it just kind of rubs electric fields over. The interesting thing here is it actually does create some friction. And because this is such a sharp tip, it actually shifts the atoms on that tip. It'll actually shift them over slightly. They'll shift back when it's done, but it's kind of interesting. Because you have to account for that. You have to take that drift into account when you're actually making your images with the scanning what is that called? Atomic force microscope. So the atomic force comes from these atoms pushing against each other. But it is the highest resolution microscope that exists. A scanning force microscope, atomic force microscope rather, can actually detect single atoms. So this is graphene. Graphene is the graphite in your pencil, kind of. So it's a crystal, and it's a crystal lattice that forms hexagonal shapes in a flat crystal. And this shows that that's theory. That the shape of graphene has always been theoretical until the atomic force microscope came along. And here they show that it is this kind of honeycomb structure with these six-sided pieces in here, these hexagons, all making this flat lattice. And what the atomic force microscope is doing is just going over this, and when it sees the carbon atoms, it's staying up high. That's the yellow parts, or the high. When it sees nothing, it goes low, and that's the red parts. So it's actually here mapping out groups of carbon atoms. I mean, there's 6 carbon atoms here. Each one of these has 6 carbon atoms. It can actually see individual atoms as well. In this image, it's actually mapping out individual atoms. Each one of these bumps is an individual atom in the crystal. Yeah, that's pretty impressive. Of course, it's not seeing, there's no such thing as seeing this, but it is making a representation of it. It is detecting it. And that's really what's quite impressive.
How long has this been around?
Oh, a few decades. Not commonly talked about because usually when these new things come out, it's usually the scientists, and usually it's physicists that are playing around with them and testing them and making them into something that could actually be turned into a product. And then once they get bored of it, then engineers take over and make a product out of it. You know, but the whole time that the physicists have it, it usually is not well known to the rest of the world that it's even available, because they're just doing pure research with it. You know, they're just finding out capabilities, you know, discovering new things, and then it's I mean, eventually an engineer will take it over and turn it into an actual product, turn it into something you can buy. But an atomic force microscope is about as big as, I mean, smaller than a computer in most cases. They're not very big devices. You can, no, you can, yeah, they're pretty simple. The only difficult thing about them is the needles. Making the needles is very challenging, because you have to have the right equipment and the right expertise to do it.
You'd hate to be the one guy that drops the needle.
They replace them all the time. And they can refurbish them. They can rebuild them. But yeah. Okay, so let's look at this problem here. In this problem, you have the skater on the ice again, but this time they're going to include some friction. Two people push. Which direction is the friction going to act in this situation? I'm sorry? Down which direction? Left or right? Left, you say? Downward and to the left? That's right. Because if this skater starts off from rest and we push on her from the left and push on her from the back, she moves upward to the right, then the frictional force is going to oppose that motion and go downward to the left, parallel to or anti-parallel to her motion, right? So that's what's going to happen. Even if she doesn't move, even if they never overcome the static force, then the static frictional force will point in the opposite direction of impending movement, or the opposite direction of the forces trying to move it. Here's another example of this, of the normal force not having to be in a particular direction. It doesn't have to be upward towards the box. Here we have somebody climbing a tree, and the friction that we're talking about is the friction between her feet and the tree. It's not a tree, it's a cliff. So anyway, she's climbing or rappelling off the cliff, and the friction is between her shoe soles and the cliff, but the normal force is from her body weight is pushing her into the wall. So the normal force on the legs coming out from the wall is opposing that force from her weight pushing on the wall. So it's not necessarily just straight down. Okay, so that is the idea between static friction and kinetic friction. A couple examples. Now we move on to friction's big brother, which is the drag force. Friction happens between surfaces. Drag happens when a three-dimensional object is in a fluid. Now that fluid can be a gas or a liquid. It can be a plasma. But drag forces are a little bit different. And we're not going to try to derive the drag force. We're not going to try to figure it out from anything fundamental. It's too much pain. We're just going to give you the equation. This is how the drag force is calculated. 1/2 times C times rho times A times V squared. What are all these numbers? C is another coefficient like mu K and mu S. It is a coefficient of drag that depends on the object that's going through the fluid and the fluid itself. So the drag coefficient is a measured coefficient. Then rho is actually the density of the fluid. The density of the fluid matters. And A is the cross-sectional area of the object going through the material, going through the fluid, but that cross-section has to be cut 90 degrees to the fluid so that if it was moving along, the fluid would be flowing through that area. So that's the cross-sectional area. And then V is the velocity. So V squared. The faster you go, the more drag force you get. In fact, if you go twice as fast, you're going to get 4 times as much drag force, right? Because that's V squared.
You said drag is created when you move through a liquid?
Fluid.
The fluid, so liquid or gas. Both liquids and gases are considered fluids. You can also consider a plasma a fluid. So here's the classic example, the bobsled, right? Bobsleds are designed aerodynamically to reduce drag, as are most vehicles are designed to reduce drag, and there's a lot of research out there done on how to do that, and a lot of people spend a lot of time and energy doing that. Reduce that drag. So what's one of the things we can reduce? We can reduce the area. So the bobsleds of yesteryears, if you go back even maybe the beginning of my life, 40 years ago, the 70s. If you go back to the 70s, the bobsleds were a lot boxier than they are now. They were bigger, they were taller. If you go back, way back, like 100 years ago, the bobsleds were open. They didn't even have a covering around them. They were just like a sled that 4 people could sit on. Dang it, I need to close this thing. But over the years, they discovered aerodynamics. They discovered that cutting down the drag as much as possible helped you to win. So they started putting covers on them. They started shaping them and everything else to allow this thing to cut through the air. But really, one of the things that they did is they sat the pushers in the car much lower. So once they get in, there's only one person who has his eyes up, and that's the driver. And the driver just barely has his eyes up. And he's laying way back. Like his feet are way up in front, so that he's almost laying down on the person behind him. So that his head is really low, just so that it's barely his eyes are fitting over the top. And that's just so he can see when the turns are coming, so that he can steer or drive the bobsled. All the people behind him, where are their heads? Down. They get their heads way down into the sled and cut down on that drag, because that reduces the cross-sectional area. As that cross-sectional area gets smaller, this whole number gets smaller, and the drag force goes down. And notice the only thing that you can do on this is to change the coefficient of drag, which means you have to change the material of your bobsled somehow, or make it smoother somehow, or whatever else. The area, the cross-sectional area. The fluid, matters, the density of the fluid, but everybody's going through air or the bobsled, so it doesn't matter. And then the cross-sectional area. So the two things that you can change, the cross-sectional area is probably the more effective thing to change. So you make it smaller. You make everything smaller. And then the other thing is that the coefficient of friction. You paint that thing with a really nice smooth paint. You are going to want to make sure that you have the best kind of materials and paint so that air flows over with very little drag, and to do some research. So here are some coefficients of drag for different shapes. Okay, so you have a circular flat plate where the circle part is facing the direction you're moving. So it's a big old plate, just a big round circle. The skydiver, horizontal skydiver, not much better than a circular plate. They don't allow the air to go around them very easily. They have a high coefficient of drag, which is good for a skydiver. Bicycle, not that much less than a skydiver. No, it's not really a bicycle with their rider on it is about the same as a skydiver. It's terrible. And cyclists spend a lot of time trying to figure out how to lower that coefficient of friction. They wear special clothes, they wear special helmets, they get really low on the bike. Like bike racers, their seat is higher than their handlebars for bike racers. Usually about 3 or 4 or 5 inches higher than their handlebars. Because that puts their head way, way down on the bike, And
Slopes.
that's right, so that it cuts down our cross-sectional area. And that's ideal. Bicycle riders are also extremely skinny, which helps. But that's not for aerodynamics, just because bicycling burns more energy than any sport on the planet. Notice that if you're a skydiver and you just jump out feet first, you go down quite a bit. You lose a lot of drag. Right? The Hummer H2, 0.64. The Honda Civic, 0.36. Right? You get the Dodge Ram pickup, 0.43. I mean, the Dodge Ram pickup has a better drag coefficient than the Hummer, but it's aerodynamics is a huge part of your fuel costs. Trucks have higher fuel costs not just because their engines are bigger, but because also they're terribly non-aerodynamic. They have a lot of drag force on them. So you can do things to help that, but really the best thing to do to help that is to buy a small car. Cross-sectional area, make it very small. Honda Civic, better than the Ferrari Testarossa, better than the Ford Focus, better than those too, right? Why? Because it's got a big engine that has to fit in there. So if its cross-sectional area is bigger. It's also a very wide car for its stability, whereas a Honda Civic and a Ford Focus are not very wide at all. I think a Testarossa is probably twice as wide as a Ford Focus. And so that adds some friction. Understandable. They did the same thing in swimming not too long ago, a couple of Olympics ago. This picture was taken just before the 2008 Olympics when they made the laser racing suits by Speedo. And these racing suits have scales on them like shark scales. And the scales are in certain places and not in other places. And it created this incredible coefficient of friction between the water and the swimmer, very low coefficient of friction. Well, they broke so many world records that Olympics that they decided to make them illegal. So they're not illegal in international competition anymore. And all those world records have little asterisks next to them now. But they were pretty amazing. It won't surprise you to know that swimmers do shave, they body shave, for the same reason, to lower their drag coefficient. And that's particularly true of hairy men. Men that have a lot of hair have to shave down when they swim. Can't wear a full suit anymore, so you have to shave. When I was swimming, we didn't wear the full suits at all, so we didn't even have it. So we just shaved anyway. But it does matter. It does make a difference, especially in longer races. The interesting thing about swimmers, even these swimmers here, each one of these swimmers has also shaved their arms for swimming, but they only shave the tops of their arms and not the bottoms of their arms. Why would they not shave the bottoms of their arms? Because the pull, you pull with your arms, and they also won't shave the tops of their feet. They'll leave, even if the hairs are minuscule. Like I have very minuscule hair on my body. My hair is very thin, very fine. You can hardly even see that I have hair on my arms or my legs, even though I'm in my 40s. And I have like 3.5 hairs on my chest. I don't have a hairy body at all. But it made a difference because those minuscule hairs, they do grab that water fairly well, especially when they're working all together. But on the bottom part of your arm, you want them to grab the water because that's your pull. The friction is required for the pull. So you actually wanted the bottoms of your arms to stay essentially from your wrists all the way to the just outside of your armpit. You want it to be completely normal so that you have the pull that you always have. So there's a lot of science into it. So let's talk about the skydiver for a quick second here. This is an interesting situation. They don't have a picture of it here. But let's draw a picture of a skydiver really quick. And let's do a quick example. So here's our skydiver flying through the air. Woo! And of course, they're moving downward with some velocity v naught, right? And they have gravity pulling down on them, which is their weight. Here's their weight, which equals m times g downward. But they also have a drag force pushing them up, which we'll call force drag. What a drag. And remember, the drag force is equal to, let's see if I can remember what it is. It's, there's a C in there. There's an A. There's a rho. There's a V squared. Did I get it all?
It's in one part.
I think it's a 1/2.
Yep. 1/2 C O A V squared.
All right. So I got it. So there are my two forces, right? When a skydiver jumps out, they're starting at some initial velocity v0, but they eventually get going faster. Later on, they have another v, maybe v1, after 1 second. After 2 seconds, it'll be even greater because they're accelerating, and that's terrible. After 2 seconds, they'll be accelerating even more, so their velocity will be even more, v2. And so on and so forth, dot, 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 all the way down. They'll get faster and faster and faster. But remember that as they get faster and faster and faster, what happens to their drag force? It increases. So the drag force gets bigger and bigger and bigger. So at some point along this path, some point in their fall here, they get to the point where they have this huge downward velocity. We'll call it V. And it's huge now. It's much bigger than it was when it started. Sorry, this is the velocity over here. I drew it in the wrong place. I drew velocity to the side. But eventually, they'll have this huge downward velocity like this. And the drag force and the so let's see, let's draw this more here. The weight force hasn't changed. But what has happened to the drag force?
Increase a lot.
The drag force has increased a lot, right? So what happens is eventually, at the beginning, the drag force is actually much smaller than I drew it. It's usually the drag force is about like this because the person is still accelerating downward. So the drag force is smaller than the weight pulling them down. However, in the end, your drag force can actually end up being equal to, but opposite your weight force. And what's going to happen when you reach that point? What's going to happen to your acceleration? If your weight force and your drag force cancel each other out, will you have any forces on you? That's right. You'll have no forces because this one will be equal and opposite to this one. You add them together, you're going to get a big, fat zero force, right?
Once you reach terminal velocity, don't you start like burning up?
No. No. Terminal velocity, when you're talking about burning up in the atmosphere, that's when you talk about coming into the atmosphere from space. And when you're coming in from space, you're moving so fast that the friction or the drag force creates a lot of heat. Because you're usually moving on the order of thousands of meters per hour kind of speeds. When you're jumping out of a plane, you never get going more than maybe a couple hundred. So, you probably get 100, maybe up to 100 meters per second.
So terminal velocity is when your weight and your drag force balance out, so you can't go
That's right.
faster.
So eventually,
So how do you get faster than that when you're re-entering from space?
because in space, you're starting in a vacuum. So there's nothing to oppose your movement in space. While you're in space, you get going really, really fast to orbit the Earth. And then you use the drag force to slow yourself down from that really, really high speed. And that creates a lot of friction. So in this case, what happens, we get these two things equal to each other, which means when you add the forces together, you get a sum of forces which equals 0, which means we're going to have no acceleration. So once you get to this particular speed, where your upward drag force is equal to your downward weight, you reach what we call terminal velocity. That's as fast as you can go falling in free fall, and you're done. I think it's, for humans, I think terminal velocity is somewhere in the hundreds of miles, like 100 and something miles per hour. I don't know exactly what it is. But we can calculate it because it is just this equation. We're going to use this equation and kinematic equation to do it. So let's go back to the book and do that really quick. So here they do it. The net force equals the weight minus the drag force, right? That has to equal mass times acceleration, which is going to be 0 because we're not going to be accelerating anymore. Weight is equal to drag force. Weight is equal to drag force. Now, what do we want to know? We want to know what speed we're going to reach. So we take this v squared that's in the drag force and solve for it. Once we solve for it, we get the square root of 2 times mass times gravity over rho times the drag force coefficient times the cross-sectional area. And we see that it depends on pretty much 2 things. It depends on the mass of the person skydiving, and it depends on the cross-sectional area. So this is why you often see skydivers with their arms and legs spread out, right? Because it increases their area. If you tuck everything in as tight as you can and dive down head first or feet first, your area becomes like 1 square foot. But if you spread everything out and you fall down chest first or back first, whatever, you end up having almost a square meter of area.
Kind of like you would never want to belly flop off of like an Olympic height diving board.
Yeah. Lots of frictional forces, well, drag forces. So here they're going to help us calculate a terminal velocity of an 85 kilogram skydiver in the spread eagle position, and it's going to be force net is equal to 0. We're going to use the weight of the diver in this equation. Here's our terminal velocity equation. M times g is their weight. And we calculate the area, approximate area. They're going to give us about 0.7 meters squared when we do that, estimate that. Throw all those numbers in, we get 44 meters per second.
How are we supposed to estimate?
So this estimation is done by saying a man is about 2 meters long and they're about 1/3 of a meter wide. So they just kind of guessed.
Oh, okay.
I think in the homework they'll just tell you what it's going to be. Which takes us to the final part of our drag theory coefficient, drag theory stuff, which is called Stokes' law. So Stokes' law is going to calculate is going to calculate the frictional for the drag force in a slow in a slow moving environment. In other words, a very, very dense liquid, or it's just moving very slowly. It doesn't really matter which. And in this case, it turns out that the mass of the object doesn't matter very much at all. It's just the density of the liquid and the speed of the object. And here they're giving us Stokes' law for an object that is a spherical object. It gets a little more complicated when it's not spherical, where r is the radius of the sphere and v is the speed of the object in the fluid, relative to the fluid. And then the nu, which is this funky looking n here, n with the tail on the right side of it, is the, what do they call that? Stokes value, Stokes constant? I can't remember what they call They're just calling it the viscosity here, but they actually have another name for it as well. But anyway, the viscosity is another measured constant of a particular fluid. And so essentially it means kind of the thickness. It's a combination of the mass and the stickiness of it is what it is, but it's measured using some weird protocol. So that is the idea behind drag force. We've got friction on our belts, we've got drag force on our belts. Let's see what else they got for us. Oh, elasticity, stress and strain. What is today? What time is it?
431.
4:31. I can't remember if I did elasticity in this homework, so we're going to check really quick. I did not put any questions about elasticity in here. I don't know why. So 29 questions already seems like a little too much to me, so I was going to take some out, but if I'm going to include elasticity, I'm going to have to take out more than that. So let's take a look here really quick and see if elasticity is included in chapter 5 in the homework, because if it isn't, then I need to fix that. Questions. Somebody's already started this homework assignment, so I'm going to have to add the questions later. I'll have to make another assignment and clear it all. So what I'll do with this chapter assignment probably is take out some of the questions which aren't absolutely necessary, and then I'll add a second chapter 5 assessment with maybe 3 or 4 questions on elasticity and stress and strain.
So should we start on any of the homework yet?
Yeah, you can go ahead and start. Whatever you want to. But be aware now, we've got now Newton's laws for movement and for staying still, and then we've got friction added in now, and we've got kinematics that can still play a role. A lot of things to keep track of.
Yeah, I watched your video that you put up for me of 29 and 30 on the last homework,
Yeah.
and I don't know, I was not getting, I guess, the correct numbers, and so I used all my attempts, and I don't know.
If you send me your work again, and I will look through it. I'll look through it again, and I'll give partial credit to people who've done the work on paper, and maybe just missed something here or there. So you can send me your work for that if you want.
Yeah, at this point, I don't even care that much about the points. I just don't know why I don't understand it.
And I can hopefully help you with that as well. So.
And the question that you answered when I did send my work, I wasn't quite sure what number, like what you were talking about in your response. So I can just go over that later with you. But
Okay. Yeah, possible that I answered the wrong question. That's entirely possible.
I mean, honestly, I don't know at this point.
Well, that happens to all of us. There's always some things we're not sure about. Okay, so now let's talk about forces that cause things to stretch, and then we'll be done with this chapter's material and we can get on to doing homework. Hooke's law. This is another guy that was in the he was in the Royal Society with my ancestor. This guy was able to put together a whole bunch of laws, equations that described the forces that stretched things and compressed things, including things like springs, but also solid materials and rocks and all kinds of things. And it kind of looks like, I mean, this is the equation right here, force equals K times delta L. And essentially what it is that every material, here's a good example, every material will stretch if you pull on it. It'll shrink or squish up if you push on it. And it will do that a certain amount depending on the material, depending on the shape, depending on the whatever. It depends on what you're doing this to. So we use this delta L to tell us how much it's going to stretch or how much it's going to squish or shrink. If delta L is a positive number, it means it's stretched. If it's a negative number, it means it shrinks. But it doesn't really matter if you just know if it's pushing or pulling on it, you can figure that out. The K is the big mystery here. Where does the K come from? Well, it comes from where all the constants come from in physics. Somebody measured it. And so the K constant is a length per unit force. Actually, it's a force per unit length is what it is, so that when you plug it into this equation, you get a force on both sides of the equation. One other thing that we should understand is what's called the tensile strength. The tensile strength of a material is the breaking stress that will cause permanent deformation or fracture of material. Well, what the heck is stress? Well, stress has a particular definition, and it is actually, if you divide both sides of this equation by delta L so that you get the force over the change in length, that's what we call the stress. K is a measured quantity that tells you how much an object is going to stress under a force. No, just how much it will stretch under a force. The tensile strength is how much force something can handle before it breaks. So here is another equation. This is Young's equation for the stress of an object. And if usually this is, let's see here. Usually this is rearranged in a different order, but they've arranged it to solve for the delta L for the stretch of the material. And the stretching of a material under a force is equal to the force divided by the cross-sectional area of the material. So in this case, you don't actually know the K. The K is hidden in the 1 over Y and the A and the L naught. It's kind of hidden in here, but it is in here. So this one is a different equation where you have the cross-sectional area, you have the original length of the material, the change in length of the material, the force, and then this Y thing, which is called Young's modulus. So if at the very beginning they give you the elastic constant, which is K, that's Hooke's constant or the elastic constant, then you go ahead and use this. But if they don't, if they tell you the Young's modulus, you have to use this equation, and you have to know the cross-sectional area of the material and the original length. But this one is a bit more scientific because it is derived a little bit more from scientific understanding than the last one. So here is a table of Young's moduli, Young's moduluses. And essentially the higher the number, the less the stretchiness, the lower the number, the more of stretchiness. You notice here that aluminum has a Young's modulus of 10 to the 9 newtons, 70 times 10 to the 9 newtons per meter squared. Big number, not very stretchy. Bone, 16, very stretchy. Do you realize your bones stretch every day? You'd really realize if you're a runner. Anybody a runner in here? No runners?
No.
Goodness, me neither. You're a runner? Okay, so what happens when you run? When you haven't run in a long time and you start running again?
Pain.
Where's the pain?
Right.
In your shins? It can happen in your muscles as well, but do you ever get it in your shins?
And splints.
Shin splints. What are shin splints? They're tiny little fractures that happen in your bones when your bones bend when you're running, right? Can also happen with jumping. Can also happen with swinging a baseball bat. Can happen with typing. All these things can stress the bones to the point that they actually form these little fractures in them called shin splints. So, cause a lot of pain. Your body knows how to fix that. It'll just fill it in with new bone. So the more you run, the stronger your bones get, the less that happens. But if you stop running for a while, you're not bending those bones very much and your bones don't get stronger. One of the reasons that some kids break their bones a lot is because they don't exercise enough. Okay? So if you have very brittle, some parents like to say, oh, my kids just have delicate bones, but they're watching TV for 10 hours a day. They don't have delicate bones, they just don't get any exercise. You have to bend your bones in order for them to splinter a little bit, in order for your body to fill in that bone a little bit and make it stronger. So, same thing happens with muscles, except it's not fractures, it's stretched holes, right? You stretch little holes in it, and you also burn little holes in it with lactic acid, right? When your muscles are burning because you've exercised, it's because the lactic acid is burning little holes in your muscles to fill up with new muscles and new capillaries.
So
Okay.
The higher Young's modulus is that the stretchier it is? Or-
No, less stretchy.
Okay.
So iron, right, for example, is 100, right? Whereas hair is 10. And marble is 60 opposed to granite, which is 45. Right? Different things, different amounts. So glass is a 70. Doesn't stretch very much. It stretches, it can bend, but it doesn't stretch that much before it breaks, right? Steel, 210. No wonder we make buildings out of it. We don't want it to. We don't want our buildings to stretch when there's force on, when they're under force, right? We want them to be really. Yeah, you can bend a little bit, but you don't want them to bend too much, right? So that's Young's modulus. And this is only one dimension. Notice that this equation only takes into account length and change in length. So this is only one dimensional. But things are not one dimensional. What happens if you stretch in 2 dimensions? Then you start using what's called shear modulus. And it's pretty much they're related to the Young's modulus. And if let's see if we can see one here. It's There's not a good example, but that's okay. But anyway, it's when you're dealing with shear modulus, you're dealing with things that are going to bend and stretch in a two-dimensional way, such that the force is actually in a different direction. So let's talk about how this works. Let's do an example first, and then we'll talk about how shear modulus works. So here's a great example, the gondola. Anybody have you ever ridden a gondola on cables? So those cables can be pretty long. In this case, 3,020 meters. So about 2 miles long, this cable in wherever this is at. And we're going to calculate the amount of stretch. We're going to calculate the delta L. And the cable is going to have a diameter of 5.6 centimeters. It's going to have a maximum tension, or the tensile strength, right? It's 3 times 10 to the 6 newtons. And we're going to assume that it's made of steel, because it does say it's steel right there. We're going to calculate the amount of stretch in that. Well, since it has a diameter of 5.6 centimeters, we can calculate that cross-sectional area we need. We can look up the Young's modulus in the table, which was the 210 for steel, right? And yeah. So the maximum stretch in the cable is going to happen when we're at the maximum tension, 3 times 10 to the 6. So that's going to be our force that we're going to put onto it. So we just plug those numbers in. First thing you got to do is calculate that cross-sectional area. You got to take the diameter, divide it by 2, and square it. And that'll give you your r squared, and multiply by pi. That'll give you pi r squared, which is your cross-sectional area right there. 2.46 times 10 to the minus 3 meters squared. And then we plug it into the equation. We have 1 over y, that's the y, 210. And notice up here that I didn't mention that this has a multiplier on it, but it does. This is 210 here, but up here the multiplier is times 10 to the 9 newtons per meter squared. So make sure that you put that on. So 1 over y is 1 over 210 times 10 to the 9 newtons per meter squared. And then we have our force, the maximum force, which is the 3 million newtons. Then we have the cross-sectional area, 2.46 times 10 to the minus 3 meters squared, and the maximum length of the cable with that maximum original, sorry, not with our original length of the cable right there, 3,020 in there. Yes.
Where did you get the cross-sectional area from again?
Cross-sectional area came from the diameter of the cable divided by 2. That gives us a radius. We square the radius and multiply by pi r squared, because we assume the cable is round. Okay.
How do we get something that's, because they moved it was originally centimeters, right? And then they put it in meters?
That's right, we convert it to meters.
Oh, okay, gotcha.
So then you get an 18-meter stretch over 3,000 meters. And it seems like a lot, but it's not really all that much. It wouldn't even be noticeable. It's a very small percent, in fact, 0.6%. How much does your leg shorten when you stand on it? So if you have a 70-kilogram person and they're supporting 62 kilograms of their mass on one leg because they're leaning to one side, we're going to assume the bone is like a uniform rod that is circular, 40 centimeters long and 2 centimeters in radius. That 40 centimeters is going to be our original length. 2 centimeters is going to be our radius, of course. So we'll use that to calculate our area. And we calculate our force as the weight of the person, 62 kilograms times 9.8 meters per second squared, that's supported on the leg. 607.6 newtons supported on that leg. We calculate the radius, or calculate the area of our bone, 1.257 times 10 to the minus 3 meters squared, it turns out to be, using the numbers given. And then we plug it all into the equation, using the Young's modulus for bone, which is 9 times 10 to the 9 meters squared. Plug it all in, and you get 2 times 10 to the minus 5 meters. So over a 3,000 long meter cable, you get 18 meters of stretch. But in your bone, you're only getting 2 times 10 to the minus 5 meters of compression. But remember, we only started with 40 centimeters of bone. So in this case, you're getting you're getting a little bit, because the original length is so much shorter, you're getting a little bit less, but still, percentage-wise, it's about the same probably. Okay, so here are the equations for or here are the definitions for stress. Stress is the ratio of the force to the area. So in our equations back here, when you have the equation with the force over area, the reason they put the force over the area, where is it? Right here. The reason they put the force over the area instead of just everything else with it on top is because this F over A is considered to be the stress. Now, if we divide both sides of this equation by the original length, yeah, that's right, which is what I was saying before. If we divide both sides of these equations by the original length, L0, we get delta L over L0, and that is going to be equal to the strain. We call that the strain. So stress is force over area, strain is original length over change in length, or change in length over original length. And that gives us our strain.
What did you say strain was again?
Strain is the change in length over the original length.
What's the measure?
It's just a ratio. It's universal. Now, shear modulus. The first one we talked about, which is the stress-strain equation with Young's modulus, the Y in there. That was just pulling on something and stretching it in the direction you're pulling it, or pushing on something and compressing it in the direction that you're pushing it. That's simple. But shear deformation is different. And the best way to describe it is to use something that is three-dimensional, like this bookcase. If I nail this bookcase to the floor so the bottom of it can't move very well, and I push on the top of it, I can actually make the top of it shift compared to the bottom of it. It's also good to do with textbooks. If you push on the cover of a textbook while the textbook is on the table, the friction between the table and the bottom of the textbook will hold the bottom still, and you'll get this textbook that kind of goes a little wonky, right? This is called a shear deformation, where the force is actually perpendicular to a length of an object, which the length in this case is the height of this bookcase, L0, and this bookcase is going to shift slightly compared to that original L0, or compared to where it was. And that's the delta x. So the L is measured in one dimension, the delta x is measured in another direction, in the direction of the force. And here is the equation for that. The delta x, or the amount of shear deformation, is equal to 1 over s now, which is another constant in our Young's table. But you still have the stress in here. The force over the area is the stress. But what is the area? This time the area is not the area from the direction which you're pushing, or perpendicular to the direction you're pushing. It's actually the area that is parallel in line with the direction that you're pushing. So it's the top of this bookcase. And then you multiply by L0 again, which is just the height of that bookcase between the force pushing it and the force holding it still. So that one's a little more complicated, but it's still kind of the same, similar kind of math. Here's another great example of a shear force on an object. This is on a nail now holding a picture on a wall. In this case, you nail the nail into the wall, and you have this force from the wall pushing up where the nail is in the wall, and the weight of the picture frame pulling down on the nail over here. And that causes this nail to shift by 1.8 microns, just a little bit of bend in the nail. So bending things is considered a shear deformation, because the force is coming from the side and causing it to deform its shape. It's called a shear deformation. So that delta x, 1.8 microns, is given to us in this case. But in this case, we're also given this L0, which is 5.0 millimeters between the forces, essentially, the distance between the two forces. Force of the wall holding one end of the nail up, the force from the picture pulling the other end of the nail down. What do they want us to do here? They want us to find the mass of the picture hanging if it bends at 1.8 microns. How do we find that mass? Well, we know that the weight downward is the force that is causing this shear deformation. We know that the wall force upward is the other force that's causing this. So we've got some things to plug into our equation. We also have the delta x we can plug into the equation. We assume the nail is made of steel. And we plug things into the equation. We look up the shear modulus of steel up here. It's in the second column here, shear modulus of steel. 80. Notice that the shear modulus goes way down from the bulk modulus. It's much harder to pull things apart than it is to bend them in most cases.
Is it easier to bend it, like, why is that, I guess?
Why is it easier to bend it?
Yeah.
It's going to depend. I mean, it depends on. It's the molecular bonding that you're fighting against in these cases. So when you're bending molecular bonds, you're just kind of shifting things around. You're just stretching them a little bit, right? But you're only stretching one side and you're compressing the other side when you're bending it. So,
And then would it be on you're stretching everything or compressing everything?
yeah, when you're doing the linear one, you have to stretch all of them or bend or compress all of them. But when you're bending it, you're stretching some, compressing others. And I suspect that has a lot to do with it. I don't exactly know the details, but that probably has something to do with bonds working together to prevent them from being broken or something. But it's probably some chemistry thing, physical chemistry thing. Anyway. So in the end, when they plug in everything for this problem involving the nail, they end up with an L0 here, the delta x. The 1.5 millimeters is the cross-sectional area part. That's what they use to calculate the cross-sectional area, is the 1.5 millimeters. And they plug it all into this equation again. No, they did it as 1.7. So yeah, here we go. So here's the radius. Take 1.5 divided by 2, square it, multiply by pi. You get 1.77.
Why do they have it times 10 to the negative 6? I know they have it in meters, but
because this
isn't there...
Because this is 1.5 millimeters, so that's times 10 to the minus 3. And when you square that, you get times 10 to the minus 6. Because you square the radius, right?
Right.
Does that make sense?
Does it be like,
Want me to write it out for you real quick?
it'd be like when you multiply decimals, the numbers always get small.
That's correct. So let's write it out real quick. So if our in this case our radius r, no, in this case our diameter d is equal to 1.5 millimeters, right?
Mm-hmm.
And that is also equal to 1.5 times 10 to the minus 3 meters, right?
Right.
So we need to take half of this to get our radius. So our radius is this times 1/2. And we're going to get 7.5 for our radius. And that's still going to be times 10 to the minus 3 meters.
Yeah, aren't there 1,000 millimeters in 1 meter?
Yes. So when there's 1,000 millimeters in 1 meter, then 1.5 millimeters is 1.5 thousandth of a meter, right? And this is what 1,000th means. This is equal to 1 over 1,000, right?
Yeah.
So that's 1,000. Then when we square r in the formula pi r squared to get the radius of the cross section, or to get the area of the cross section, we get pi 3.14 times this 7.5 squared. But it's 7.5 times 10 to the minus 3. And when you square the 7.5, you get something like 60-ish, right? And when you square the 10 to the minus 3, you get 10 to the minus 6. So you get 60-something times 10 to the minus 6.
Isn't the radius half of the diameter?
Yeah, that's what I did right up here, where I took the radius of
So,
sorry, this is 0.75. So half of 1.5 is 0.75. I'm sorry, I wrote that wrong.
it's okay. Well, what I did is I just did 0.75 squared, and then I took it times pi, and then I was going to convert, but I don't, like, I divided it by 1,000.
Whenever you're converting areas and volumes, always do the conversions before you calculate the areas and volumes. Because even though there's 1,000 millimeters in a meter, there are 1,000,000 millimeters squared in a meter squared. And this is why. I'm going to draw a meter stick here. Here's my meter stick, right? And it's got 1,000 of these little millimeter marks on it, right? But if it's 1 meter squared, there's another meter stick over here with 1,000 little millimeters, right? And for each one of these little millimeters, there's a square millimeter out here. And it turns out for each one of these, there's one as well, right? And in between, and it turns out it's 1,000 times 1,000 of these squares in a square meter. So there's a 1,000,000 square millimeters in a square meter, not 1,000.
Okay. Thank you.
I recommend that you do all of your converting first and then do your calculations. All right. Now, it just so happens that the world is not two-dimensional either. It's also three-dimensional, right? And you can stretch things and compress things in all three dimensions. And this is what we call bulk modulus. So if you put something under stress in every direction, and you squish it from all directions, or you stretch it in all directions, it will expand in all directions, or it will compress in all directions. And the equation is pretty much the same. Instead of a y or an s, we have a 1 over a b. Instead of a cross-sectional area, we have a volume, an initial volume, and a change in volume. And this is usually the case when you have something that is immersed in a fluid. It can be a liquid or a gas, and that liquid or a gas is pushing on it from all directions. And it can push on it in all directions towards it, or the object itself can actually push on its surroundings in all directions. So in the example of your body when you go underwater, the water pushes on your body in all directions, and you can really feel it in your lungs because the water will actually compress your lungs, and that's what makes it hard to hold your breath. Is the water is compressing your lungs and squeezing the air out your mouth and nose. It's trying to squeeze it out of your body. People who are used to swimming a lot get very used to that feeling and get very strengthened against it, so they can hold their breath a lot longer without being uncomfortable. Because you can go without breathing extra oxygen with a lung full of air. You can go without breathing for 5 or 10 minutes. But the discomfort is very difficult for most people. The discomfort of having that air trying to escape out your mouth and nose is very difficult. So you have to really condition yourself and get strong at holding that air down in your body.
I thought it was the rule of 3 between sit on for 3 minutes without air.
I'm not saying without air, I'm saying without breathing new air into your lungs. You have enough oxygen in your lungs to process, and you can keep processing that oxygen as long as your blood is pumping. And also that my numbers count hyperventilation. So you start by hyperventilating and filling your oxygen in your blood cells to 100%. So if you hyperventilate first for a few minutes and completely saturate your blood with oxygen, super saturate it with oxygen, and then take a nice deep breath, and if you have big lungs, the maximum is between 5 and 10 minutes. I think the record is around 8 or 9, something like that. I don't know exactly what it is, but it's a pretty long time. Held by a Navy SEAL, I believe, because they practice that. They have to learn that. That's something that they have to know how to do. Most divers have to learn how to do it, and most swimmers can do it. I had a swimmer on my swim team who could swim 3 laps of a pool underwater on her back without coming up for air. So that's right there, a minute and a half of high exertion, swimming hard. So that's a long time when you're swimming hard because you're burning that oxygen. If I'm just sitting still underwater, I think my record is 3 minutes, just sitting still, and I don't really practice it that much at all. But what's that?
And with, there's also a difference between heat and cold. If you have hot air, it's a lot harder to keep it in than cold air.
That's right. Hot air is moving a lot more, so it's higher pressure. But as it cools off in your body, so if the air is hotter than your body when you start, as it cools off, it makes it easier, but there's not as much oxygen in it because it went into your body at higher pressure. So, yeah, there's a lot of differences that are made, but the idea is that, but the other thing is that this is the pressure outside of something is lower than the pressure inside, then that can also make a difference. So your body gets compressed when it's underwater, but a balloon actually expands when it goes up higher in the atmosphere. Because as it goes, so if you have let me show you an example here really quick. The Bright, what's his name? Bright, I think that was his name.
Those are expensive watches.
Yeah. So this was a balloon that set the record for orbiting the Earth for going all the way around the Earth without stopping. And these are some other ones that set some records, but all of these balloons are designed to be kind of this teardrop shape at lower altitudes. And as they go higher, they actually have room to expand. You can see it here when it's not expanded. It's all droopy and has all this extra fabric, and then it expands as it gets at higher altitudes. And it's designed specifically to do that. So, very interesting designs. Okay, and weather balloons, for example, when you inflate them at normal altitudes, when you're just launching them, they're just a big teardrop. But when they're at full altitude, they're a sphere. They're just a big ball.
Before it pops, right?
Yeah, before they pop. Yes.
Is that why it's extremely dangerous for you to be underwater when an explosion happens underwater? Is the pressure? Because I hear if you're underwater when an explosion underwater happens, it can destroy your lungs.
The reason for that is because the pressure is transmitted through the water much more effectively, much more efficiently. Than air. Air, it dissipates rather quickly because air moves in random directions more than water does. So pressure waves travel faster through liquids and solids than they do through air, and they also travel more organized through water and through metals. So that's more of the reason. Sound travels faster and more efficiently through water and through solids. So, anyway, we're going to learn more about that later in the semester. Okay, so that is the idea behind the bulk modulus expansion. And here we're going to do an example of a change in volume with the, of an amount of water. So in this case, we're not talking about some enclosed thing. We're just going to calculate how much water gets compressed as you go deeper and deeper and deeper into the ocean. And so the fractional decrease in volume is defined as the change in volume over the volume, initial volume. And we want to know how much smaller a certain amount of water gets, percentage-wise, or fractional-wise, when you go down 5 kilometers below the sea. So that's pretty deep in the ocean.
I thought water didn't, like, water as a liquids don't, they can change their shape, but not their volume.
They can change their volume, but we assume that they don't to make the math easier for when we're doing things like hydraulics. They assume that they don't because it makes the math for hydraulics very easy, but they do.
Okay.
They call them incompressible fluids, but there's no such thing as an incompressible fluid. There's no such thing as incompressible anything. Everything can compress. It's just very, very small, as we will see here. Even 5 kilometers deep, it's not very big, not very much. But here they tell us the force per unit area, or the force over the area, is equal to 5 times 10 to the 7. So in our equation here, we have a force over area, and that fraction is going to be replaced by a single number, that number being 5 times 10 to the 7th newtons per meters, because that's force per unit area. So F over A in this equation is going to be replaced with one number. So when we plug in the one number for F over A, we get that 5 times 10 to the 7 right there. And then the 1 over B is going to be the bulk modulus for salt water, and we're calculating delta V over V naught. So we just divide these two numbers, and we get 2.3%. So the volume is going to drop by 2.3%, 5 kilometers under the ocean. Doesn't seem like a lot, but that's enough to cause serious problems to the human body, like crushing depth for human body. Okay.
There was a book I read, it was a fictional book where like it was about divers and like somebody who had acclimated going all the way down. Like,
Yep.
So their body would get used to it. And somebody used a diving suit who happened to be the antagonist, the bad guy, and like threw a rock at it, punctured the suit, and go.
Yeah. Yeah, they call it crushing depth. You get to a certain depth under the water for a particular vessel or body or whatever. And for us, the crushing depth happens when our lungs collapse. When our chest cavity is held open by the air in our lungs when we get down to certain depths. When we're in the air, our chest cavity is held open by the vacuum between our lungs and the wall of our chest. But when we're underwater, our ribs are literally being held apart, being held open by our lungs. You know, without the air in our lungs, our ribs would literally collapse if we get too deep underwater. And it's not very deep. It's only, I mean, you can only go maybe 50 feet deep before you start getting into trouble with that. You start feeling that pain. I don't know if any of you have been 50 feet deep, probably not, but you know, the furthest I've ever gone down is probably about 40 feet. And it really starts to hurt at those depths. And this is way deeper. Submarines don't even go this deep. You know, you have to have special research vessels to go down this deep. Most submarines don't go more than I think they go about 1,000 meters is what submarines are designed for. So about a fifth of this. So that's getting really far down. But 2.3% crush. I mean, that's like, yeah, that'll hurt.
So I know that divers can go deeper than that, but how do they do it?
So what you do if you want to go diving that deep is you have to change. First of all, you have to change the pressure of the air that you're breathing, so that the pressure of the air in your lungs is much higher, so that it can counteract the pressure of the water that's crushing down on you. But in the process of doing that, of increasing that pressure, you have to increase the vapor pressure of the oxygen in your blood. So you have to slowly start breathing higher and higher pressure. They put you in a chamber. They put you in a chamber called can't remember what it's called, but it's a pressure chamber. And they just slowly increase the pressure a little bit at a time. And some, depending on how far you go down, you have to spend longer and longer times in there. If you're going 5 kilometers down, you're going to have to easily spend a half a day in there. Just slowly increasing the pressure, slowly increasing the pressure, slowly increasing the pressure. The pressure outside and the pressure inside your lungs will be the same, so it won't feel any different to you. But what's going to happen in the end is that the pressure inside your lung will be able to withstand the pressure from the water outside. And then then they'll send you, they'll either do that before you go down on the top of the surface, or while you're going down, or when you get down there. You can do it whenever you want to. But you have to do it, you have to spend all that time in they call them a decompression chamber is what they call it. But a compression chamber or a decompression chamber. But anyway, once they've equalized that pressure, then you're going to go into, say, a research diving bell that has that high pressure gas in it, that high pressure air. But then at that point, you can just put on normal scuba gear and go swimming out in the ocean, and the pressure outside and the pressure inside are going to be equalized. So it'll be just like swimming in a swimming pool, except it'll be really cold. So you have to wear a dry suit. So you have to wear a dry suit with a heater in it just to keep you from freezing. But besides that, that's what it's like. So, good question. So that takes us to the end of the chapter. We covered friction, we covered drag, we covered elasticity, stress, and strain. And we are done for today. I will get the second homework assignment up. It won't be very long, just cover a couple of problems for stress and strain, probably 3 or 4. And then I will remove some of the questions from the original assignment. And then I will get to work on the test. And by the time we meet next, hopefully all 3 of those things will be done.
So what are we doing for the rest of the week?
The rest of the week we will do like we normally do. We will meet and do a lab tomorrow. And then we will meet and do homework review on Wednesday.
Okay.
And then we'll have a test next week. And then for the rest of the semester after this, we will try to cover 1.5 chapters about per week. We will, instead of just doing a chapter one day and a homework the next day, we'll try to do a complete chapter on one day and maybe do some homework review as well. And then maybe finish up the homework review the next time and start a new chapter. And so we'll be a little bit off kilter a little bit for the rest of the semester, but we'll try to cover as much as we can every day for the rest of the semester. These first 5 chapters are probably, there's a few chapters after this that are kind of equal in difficulty to these chapters, but after we get to about chapter 8 or 9, it starts to become pretty repetitive and much easier, and we're just kind of going to crank through a lot of problems after that. So.
Okay. And we'll have, after we get that test set up, we just have to go into some place where we can have a proctor.
Yep, you take the test with a proctor, and as soon as I get it set up, I'll set it up with a due date. It will have, you won't be able to use notes, but you can use your book online. You can open up 2 windows, for example, but please don't open more than that. It'll also be timed. It will have a timer going on it. You can actually close the timer if you want, if that makes you nervous, but it will have a timer running. And I usually make it for 2 to 3 hours, depending on the questions I put on the test. But it's usually about 10 questions on the test, covering a couple of questions from each chapter usually. Usually I'll put one, usually about half the questions on the test will be questions that you have to calculate something about. The other half will be questions that are more
Concept?
yeah, conceptual types. You know, you're choosing something, you're matching something. And usually I'll have 2, maybe 3 questions that are kind of medium difficult. I'll have 2 to 3 that are a little bit easier of those questions, of the ones that you actually have to calculate things with. So it's usually about half and half. And it's usually designed, what I do is I see how long it takes me to take the test, and then I multiply that by like 5 or 6 for my students, and that's usually about sufficient. So it usually is set up for a couple of hours 2 to 3 hours the most. And besides that, you can use your calculator as well, pencil and paper. Any other questions before we sign off for the day?
Just a question about
Did you have any more questions, Cassidy?
Yeah, I just wanted to go over those ones with you that I had trouble with over the weekend,
Okay.
but
Which ones?
otherwise, no.
Which ones were those?
The one with the picture I sent you in my messages, number 9.
Okay, so that one you were doing the problem right. The only thing that I could see, I mean, I pointed out that one little error that you made. I can't remember exactly what it was. Question 30, was it?
It was number 9 in chapter 3.
Did you guys have other questions, or are you going to just take it off?
I just had a question about what I was doing this next week, because I'll be out of, I'll be at the National Speech and Debate Camp
Right.
for Monday and Tuesday for sure, and even if I get eliminated at the first cut, I'll still be in transit back,
Sure.
so I miss class all 2 days.
Yeah, so next week will be chapter 6, which I believe is, let's take a look really quick. Circular motion and gravitation. And we will probably get through most of, we'll probably get through all of chapter 6 and part of chapter 7 next week. So be prepared to just go through, and I'll record the class like usual. But we'll be through chapter 6 and part of chapter 7 next week.
So, it will kind of depend on how far into the tournament.
Yeah,
If
that's
I make
fine.
it all the way, finals are on Friday. If
Yeah.
I make it that far, I'll be completely honest, I'm not going to be looking
Yeah,
at anything.
totally understand. Just tell me.
I'll look at it for sure over the weekend,
Yeah.
and I might send you an email soon if I can get together just to have somebody go over that
Sure.
much information.
Sure, yeah, that's fine. Just keep me apprised of the situation so I know what to do for you to help
Okay.
you through that.
Thank you so much, Mr. Day.
No
And,
problem.
I'm trying to get a hold of whoever was putting me on the calc-based physics waiting list.
Yeah,
Because I thought they were here, but they're in the Cook one.
Okay.
Lana or Elena. I can't remember
okay.
her name. So
Lana.
we're going to be trying to work on that. And
Okay.
at this point in the semester, my parents said I'm also going to be looking at whether or not I should just maybe wait until I take it or what I want. So
It's up to you.
yeah. I think I'm still going to try to convince them to let me take it. But
Well, you might as well so you can get the credit for it and not have to take it again.
Yep, exactly.
All right.
So, Mr. Daly, how-
See you later. Okay, let's look at this one. Let's go back to this one. So this is
Well, when you answered my message, you gave me a number you said I was supposed to use, but I don't see that number anywhere in my prior calculations.
Oh, yes, I remember that. Let me look at my email really quick. Wait, did you do that through My Open Math or through email?
Yeah, my open math.
Okay, let's go look through. I remember that. Sent messages.
Because after I did the physics lab, everything kind of clicked, and so I tried to go back and do this,
Yeah.
but I still wasn't getting the numbers for part D.
Oops.
Yep.
Yes.
I know it's sideways. Sorry.
Okay, so here, let's see. I said you put 3.78 for VY0, so that's this number right here, right?
Well, I put it with the sign, so either way, I was going to get velocity of y. I get 1.96 for my initial velocity of y.
Right. Okay, let me look at something really quick. Oh, you know what I think I did? Wait, is this your homework? Read book, detail. I don't see your name's not on here. Where's your name? This is not you.
I don't know.
Um, so here's number 9. So you got the velocity to be 5.35 meters per second off of there. And this is the one right here. That's where I took that number from. 2.93 is the answer that was correct in part C.
Oh, am I doing a different?
So in part C, you actually got the answer correct at 2.93. You calculated that correctly. And that's the number you should use for your y velocity in part D.
Oh, I must have done a different example. That's why.
Oh.
I must have like asked to click the button for do a new problem.
Oh, that confused the heck out of me then, I guess.
But even with my new example, I don't know. Here, I can just do that one quick.
Yeah, sorry, I thought you were using the same numbers, so I was looking at the
Well,
ones
I
you
thought
already
I
done.
was too, but I didn't check my.
So let's see. Answer's supposed to be 0.71. Well, that would explain why the time was off too. Because your time. Yeah, that'll explain your time too. So that was confusing.
Well,
Okay, so yeah, but everything else that I'm seeing here, I'm seeing you doing it correctly. I mean, all of the math is correct. I don't know if the arithmetic is correct, but you've got the correct equations in the correct places.
so when I go back to my reattempt question, it says I'm supposed to get like 0.71 on part D for the time. And I'm getting like double that. I'm getting 1.4.
Yeah.
And I don't.
And I was looking for a factor of 2 in here somewhere, and I couldn't find one. I checked your quadratic, and that's correct. Oh no, it's not. Here's your problem right here. So in this quadratic right here, can you read that sideways? The thing that's in front of your t squared is your a. The thing that's in front of your t is your b. And the constant term is your c. And right here it doesn't matter, and over here it doesn't matter, but right here it does matter. This should be 2 times negative 4.9. And so not only is it going to give you a different, not only is it going to give you a different number to calculate, but it's going to give you a different number that's correct, because it's going to change the positive to a negative and the negative to a positive here, but it's also going to divide it by 4.9 instead of by 1.1, right?
Yeah.
So that's another mistake right there that I didn't notice that before, but I just did now. So.
Okay, that makes so much sense. So that's probably where it all went
that's very
wrong,
likely.
because I was doing everything correct, except that.
Yeah, all the mathematics is correct. Just a little bit of calculation error, which is very common. it's hard to calculate so many things. Physics is a science of organization and calculation. Right?
Yes. Okay, so I'll do that by myself and go through that, and I should be fine.
Okay, do you have any other questions at all?
When I was watching your video, I don't know if it was, I don't know why, but I was just struggling to follow you.
Okay.
And
What would
so,
help?
let me find it. It was number 29 from chapter 4, I think.
In the homework?
Yeah.
Okay.
Let me find it. It was either 29 and 30. Yeah. Well, I didn't get either of them. But
29 and 30 from chapter 4.
yeah, 29 first. I understand that there's the weight parallel and the weight perpendicular.
Yep. So this one right here.
Yeah.
Yeah, these two are easily the two hardest problems, and I'll be honest with you. Most people chose to several people just chose to skip them, since they're only worth 1 point. But that might hurt them on the exam.
Well, I mean, I ended up using all my attempts, and so I didn't do too hot on them. But I don't care as much about my grade on my homework as much as like understanding it.
Yeah, sure.
And so I'll ponder these things even after homework is over, because I want it to click.
You'll really know that you've arrived as a physics student when you start dreaming it. And
I don't know if I want to.
I'm not kidding. By the end of this semester, you will at least have 1 or 2 dreams about physics problems. And they may just be nightmares, but they will still
I loved chemistry, and I don't know, it clicked with me, and this is just so different. Like, it's not, but it is.
That is very common. It is very common for physics majors to say that about chemistry, and for chemistry majors to say that about physics. So we're talking 2 science people, in related science fields that hate the other science field, because chemistry did not click with me. Well, click is the bad word. I understood chemistry just fine. It wasn't any problem for me. It didn't challenge me in any way except for memorizing things, because I'm terrible at memorizing things. But mostly I just hate memorizing things. I can do it just fine. I just don't like to do it. But
for me, it's hard to visualize things.
Yeah, see, and that's the thing about physics, is learning how to draw something out is very important in physics, and learning how to organize thoughts. But physics has always I've always loved it, and it always really melded with me really well. Chemistry, not so much. I took my 1 chemistry class in college and never looked back. I never took another one. So it is kind of a personal preference thing. It's very much that way. So we got our wheel here. We got our cable. Our 2 boxes. Right?
Yeah.
Now the thing about the weight that confuses everybody is this tilted axis. Because this box is going to be moving in this direction that is parallel to this platform, we don't want to work in X and Y like we normally do. We don't want to just work in the normal horizontal, vertical directions, because then all of the movements are going to be all wonked up. We're going to have components of everything, just messy. We'd much rather just tilt our axes so that we say that we have a horizontal or a parallel axis rather, and a vertical axis that's perpendicular to that. And it's just like we tilted the world. However, even though we've tilted the world, the weight of this box still pulls straight down towards the earth, right? Mm-hmm. So that weight vector still pulls straight down. However, part of that weight vector is in the perpendicular direction, and part of it is in the parallel direction. So we draw the components. The parallel direction is the one that pulls it down parallel to the surface. So we draw a force that's parallel to the surface downward towards the bottom. And that's the weight, that's the part of the weight that is parallel. That's the part that's going to slide the box down, or try to slide it down. And then there's another part of the weight that is perpendicular to this. So we draw a force that is perpendicular and downward to the left. And that's our weight that is perpendicular. And because these two things are 90 degrees, there's our 90-degree angle, right? Here's our angle theta. That's the smaller angle, and this is our angle theta in here as well. Because it's the smaller angle, right? So those two are our components of the weight vector now. That is straight down towards the Earth, but the components are parallel and perpendicular to our surface here, right? The advantage of this is we own this vector here, this weight parallel vector, is the only vector that's adding tension to the rope. The perpendicular vector is just holding the box down on the surface, right? But this parallel vector is actually pulling the rope downward to the right. So it's adding to the tension in this rope, right?
Right.
So in this, for just this box, we'll call this box 1 and box 2. For just box 2, if we draw a free body diagram of box 2, we have a tension force that's pulling upward here this direction. Call that tension. We have the weight parallel force, which is pulling us down in this direction. And those are the two forces that are on that box, box 2. For box 1, we have the same tension force, because it's connected to the same rope, pulling up on box 1, right?
Mm-hmm.
And we have the weight pulling down. This is the weight of box 1. This is weight parallel box 2. And those are our two things that we're going to create equations for, right?
Right.
Now, if these things are accelerating, they're going to also be accelerating at the same speed, right? Because they're connected by the rope. If they're accelerating down this way, they're going to have the same magnitude of acceleration. They'll be in different directions, but it's the same magnitude. So we can set up the equations the same as well, right? So let's set up the equation for box 1. The sum of all of the forces, which means the tension force, which is up, it'll be positive. The weight force is down, that'll be weight 1 down negative. That's all the forces. It has to equal the mass of box 1 times the acceleration of box 1, which is going to be just the acceleration, because they're both the same. So that's one equation, right?
Right.
For this other one, we have the tension, which we'll call this direction negative for the tension to the left.
Yeah.
So that'll be negative tension. And then we'll plus W parallel 2. But W parallel 2 has a value over here because of this trigonometry. This is opposite the angle. So it's going to equal the weight of the box 1, or weight of box 2, times the sine of the angle theta, right? So we can just substitute that in our equation. So this would be plus sine, or sorry, undo.
Weight 2 times
Yeah,
sine of
that's
theta.
right. Plus weight 2 times sine of theta. Weight 2 sine theta. And that has to equal mass 2, because we're accelerating the second box. Mass 2 times the acceleration, but the acceleration magnitude is still going to be the same, just a, right? Well, it's just the same number, even though they're in different coordinate systems and different things. They're connected by the rope, right? Now, the beauty of these equations is we have two things that are the same in them. We have the tensions and we have the accelerations, right? And what do we want to solve for? What does it want to know? I haven't checked that. What is the net force on the system? Magnitude of the net force on the system. So what we need to find out is we need to find out the magnitude of the tension and the direction of the tension. Okay? So the tension, the negative tension was this way, which was positive tension, which was negative direction for this one. This one's positive tension this direction. So we need to solve for the tension and figure out which way it's going, which way this thing is going. Okay? That's what we need to do. So we're going to solve for T. Probably the best way to do this is to solve one of these equations for T or the A or something and plug it into the other equation. I'm going to solve this one for A. It's just simple. I'm going to just divide by M1. And I just get that right there, right? And then I can plug this in over here, right?
See, I don't understand that. I think this is where I get mixed up, is these equations,
Okay, so
like getting ready to solve.
whenever
Because we don't know tension or acceleration, so how can you solve for it?
So when you have one equation and one unknown, you can solve for the unknown, right?
Yeah.
It turns out that if you have two equations and two unknowns, you can solve for both unknowns if you solve for one of the unknowns in terms of the other one and plug it into the other equation. So this is a little trick that we learned in college algebra. If it's been a while for you, it's something that you probably just forgot. But you can solve this one for one of the unknowns. So I'm going to solve this equation for A, even though I don't know it. I'm going to plug it in over here so that I get a T minus W1 over M1 for A over here, and then there's no A in this equation, right? So let's do it really quick, and the A will disappear, and then I can just solve for T when I'm done. So when I do this, I'm going to get negative T, that's this one right here, plus W2 times sine theta on the left side. And on the right side, I'm going to get M2 times A, but instead of A, I'm going to put in this big thing, T minus W1 over M1.
Yeah, I never learned how to do this. So.
This is called solving by substitution, solving multiple equations with multiple unknowns by substitution. Be glad I didn't give you a problem that has 3 equations and 3 unknowns, because those get really painful. But this one is not so bad, because now we just need to solve this equation for T, right?
Well, I guess we did these, but it wasn't, I guess, this complicated.
Yeah. I'm leaving a lot of letters in there because I want to be able to follow my work if I make a mistake. And I'll plug in the numbers at the end. But essentially, from here, I'm going to multiply both sides, everything on both sides of the equation by M1. And then I'm going to multiply out the M2. And then I'm going to get all the T's on one side and everything else on the other side and clean it all up. And then plug in my numbers and be done.
So that's another thing, is when you get your, when you have,
You want to do it really quick so you can kind of see the process?
yeah.
Okay. So let's go ahead.
Sorry.
No, it's okay. I'm going to go ahead and multiply both sides of my equation by M1 here, because that's just going to get rid of this little fraction over here, right?
Mm-hmm.
Over here, I have to multiply 2 separate things, the negative T and the W2 sine theta by M1, so I put some parentheses around it, just to make sure I do that. And now I have M2 times T minus W1 on the right side. So I'm going to go ahead and multiply that out. No, I'm not. I'm going to divide by M2 as well over here, just to clean it up even more. Does that sound good? If I divide by M2 over here, then that's good enough.
Yeah.
Then I'm just left with T minus W1 over here, right?
It doesn't have, the M2 doesn't have to be over the entire left side, it's just over the M1.
This one? This is the entire left side because there's parentheses around this, right? So over here, I've got T minus W1 on the right side. And if and then I've got all this other stuff on the left side, right? All this stuff over here. So if I add W1 to both sides, then I'll just have T on the right side. But then I've got this big mess over here, and I've got a T in the middle of it, right? So now I have to multiply the t times m1 over m2, the negative t times m1 over m2. I have to multiply this w2 sine theta times m1, m2, and I'll get a big mess over there. So let's do that. I'm going to move everything to this side over here. I'm gonna have a w1 on the left side, so I'm going to write that down. w1. And then I'm going to have m1 over m2 times negative t, so it'll be negative m1 over m2 times t. Right?
Yeah.
And then I'm going to have a plus m1 over m2 times w2 sine theta, right?
Yeah.
And that's all equal to t, right?
Yes, sir.
Then all I have to do is add this term to both sides, and I'll get the t's on one side, right? So if I do that, then I'll have w1. I'm going to add m1 over m2 times t on this side and get rid of that. And then I'll still have an m1 over m2 times w2 sine theta. But on the right-hand side, I'm going to have t plus m1 over m2 times t. Then I'm going to factor out the t on the right-hand side. I'm going to move up here now, so I don't have to make a new page. Because if I make a new page, I have to memorize all of that, and I don't want to memorize all of that. So I'm going to have all the stuff that I had on the left-hand side. I'm just going to write it as a squiggle. And the right-hand side, I'm going to have t plus m1 over m2 times t. So I'm going to factor out the t. That's going to be t times 1 plus m1 over m2, right? And then I just divide both sides by 1 plus m1 over m2. And it gets kind of messy on the left-hand side, but it's manageable.
Yeah, so the m1 over m2 cancels, doesn't it?
Nope, they're different masses. So it's m1 over m2.
Weight 1 plus m1 over m2 times weight 2 sine theta divided by m1 over m2.
It's going to be divided by 1 plus m1 over m2, right?
Oh, okay.
So if I erase some of my graphics here, I'll finish this really quick. So if I divide everything on the left-hand side by 1 plus m1 over m2, then this is what I end up with, is I end up with, on the left-hand side, weight 1 plus, oops, weight 1 plus, there we go, m1 over m2 times w2 times sine of theta. And then I put parentheses around that whole mess so that I know that's all on the top, and I divide that whole thing by this thing right here, right? 1 plus m1 over m2. That always looks like a 2 even though it's a 1. There you go. m1 over m2, right?
Yeah.
And then that equals the tension. So there's your formula for the tension. A little bit messy, but it's doable.
Maybe that's why I think that's why I was so lost, because I didn't understand how to
This solving down here.
solve.
Yeah. Yeah, so that's a trick that we use quite a bit in physics, because we're often getting different information from different parts of the system, but they're tied together because they have the same acceleration, for example, or the same something. So that's what ties the two equations together and makes them solvable.
Okay. So then once I know tension, I can go back and find acceleration.
Yep.
And then I can find which it's weird. The questions ask about, the first question asks about the net force,
Yep.
but you're not able to find that first.
No, no, the net force requires you go through all this mess. So sometimes they don't ask you the questions in order, and they do that on purpose so that you can think about what you need to get what you're going to need first to get what you need later. It kind of forces you to think the problem through after you've got all the information. So, yeah, for sure. And from now on, they will do that a lot. They'll do that a lot from now on, where they'll ask several questions, but you might have to get the answer to question C to get the answer to question A. It's part of the physics. So,
Probably where I bumbled too, because it's been in order for the most part since the beginning.
yeah.
So now it's.
And they kind of, and again, they kind of do that on purpose. Remember, I warned you that physicists love trick questions, and that's actually kind of a dirty trick question because it's not really a question. It's just the order of questions. But it is a trick because they're trying to get you to not stick to doing something the same way every time, but thinking what way it has to be done in order to get the right answer, right? So it's part of the problem solving process. And it's actually interesting that you noticed it because some students don't, and then they just don't do the problem. And I suspect that's why some of the students didn't do this problem, is because they didn't figure out that it's not in order. So
I felt like, I don't know, and I just felt like the entire time I was doing it, I was thinking, I bet the other students have it. I bet they understand
no.
it, and I'm just.
No, I don't. I think I'm not sure how many students actually got this, but I don't think anybody got it completely done. And I think a couple of students left it completely just blank. So it's you're not alone. This is a tough one for sure. But your grades are looking good, so I wouldn't worry too much about it.
You know, I didn't feel. I mean, I know they are good, but I just felt defeated because I just think that all the other students are getting it, and I'm completely lost sometimes.
You're not the only student that's struggling. Every one of them is struggling. My son, who has been around this his entire life, because he's lived with me his entire life, is struggling with it. You know, I've helped him a lot with his homework as well. So it's have you ever heard how they how they do boot camp for the Army and the Marines, where they break them down and they humble them until they're just nothing, and then they build them up from there? That's kind of how physics is, except for the brain instead of the body.
I'm exhausted.
Yeah, and it's supposed to be that way. We're trying to teach you a way of solving problems, an approach to solving problems that you've probably never experienced before. And it's not really about the physics for most people. For most people, it's about the solving of problems, because most students rarely get an opportunity to solve problems like this before they leave school. But physics gives you that opportunity. Once you leave school, you'll be solving problems like this all the time. Not mathematical problems, but life problems and organizational problems and people problems and whatever else. But they have a lot of facets to them and a lot of things you have to organize and get right. So, but I wouldn't feel like you're the only one struggling. Everyone struggles with this. It's a hard class. So.
Do you have to be somewhere after that?
No, I'm okay right now. What do you want to do?
Could we go over 32?
Sure.
Or number 30 also.
Yeah, let's let me see. Let's clear this. Where's my clear button?
Because, like I said, I watched the video and I watched it a few times, and I ended up crying at my boyfriend's house over it. I was like, I don't get this. And it was so nice of you to do that for me. So I hate asking you again.
No,
but that clicked.
No, that's what I'm here for. I get paid for this. It's not like I'm doing this as a charity. I do get paid, so I do get paid. And even if it was for charity, it doesn't bother me. I enjoy teaching. So number 30 is this one, right?
the mass hung on the wires with static equilibrium.
Oh, are you not seeing my screen right now?
No, it's whiteboard.
Okay. Let's go back to screen. So this is number 30, right?
Yes.
So we've got the two cables holding up this mass. They want to know it's in static equilibrium, which means it's not moving at all. And they want to know what is the tension in line 1, which is this one right here. Is that the question they asked you?
Yes.
Okay. So
The one you have is what I have.
okay, so this one right here. All right, let's go back to our whiteboard and draw the picture. So the picture looks like this. We've got our, it's like we're playing hangman. Right. We got this guy, we got this one, we got this one. And I deliberately leave numbers off because it's better to just write things than it is to put in numbers. And then we have an angle up here of theta, right?
Mm-hmm.
And we want to know what tension in line 1 is. And it's going to be, we're going to have a free body diagram. So I'm going to do my free body diagram around this point right here.
Mm-hmm.
So that's my point of interest, because that point is the point that everything is acting on. So we have tension 1, which points up in this direction. Tension 1. And we have tension 2, which pulls off in this direction. Tension 2. And we have tension 3, which comes from the weight of the box down this direction. So we'll just call that weight, which equals mass times gravity, right?
Yes.
And we'll call it negative mass times gravity just so we know it's downward. And this one, this tension 2, is going to be completely in the x direction. It has no other components, right? This is our x direction. This is our y direction. This one's completely horizontal. But this one has two components. It has an x direction component, which is going to be a negative. So this will be T1 in the x direction, which will have a negative value to it. And then it has a y component up this direction, right? T1y, which will be a positive direction component, right?
Right.
And the angles here, this angle here is going to be, let's see, it's going to be the same as the angle that they gave us, theta here. Do you know why?
Because of they're on the same line. They're
That's correct. So they have,
corresponding,
yep, so
or not corresponding. They're
they're opposite angles.
opposite.
Yeah. So they're these angles that are opposite each other on this line, between parallel lines. So that's the same angle. So
Yep.
that's good. So that is the adjacent angle to here. So that tells us right away that this is going to be equal to tension 1 times the cosine of theta, right? And then this one would be opposite that angle, because it would be over here if we moved it, but it's opposite the theta here. So this one would be tension 1 times the sine of theta, right? And the number,
Right.
and the number that we're looking for is tension 1, right?
Yes.
So now let's do our problems in the x and the y direction. Remember, we can split this into x and y directions. In this case, the sum of the forces equals mass times acceleration. What is the acceleration of this box?
0.
So the acceleration part is going to be 0, so the sum of the forces equals 0 in the x and the y direction. So here's our x direction, here's our y direction. In the x direction, what forces do we have? This is negative, by the way.
In the x direction forces.
Yeah, what are the x direction forces? There are two of them. They're going left and right. Which ones are they? Well, which forces are going right from here? We have T2 is one, right?
Yeah.
So that's going in the x direction. That's an x direction force. What's the other one that's going along that same line?
T1x.
T1x, which is a negative T1 cosine theta, right?
Mm-hmm.
Equals 0. Do we know what T2 is?
It's
We don't know what it is, do we? That's an unknown. Do we know what T1 is? No, that's what we're trying to figure out. The only thing we know in this equation is theta, so we're not going to be able to solve for anything here unless we have another equation, right? So let's do
those
the...
two equations. Can
do.
solve two unknowns.
That's right. So what are our y direction forces?
We have the weight.
The weight, which is a negative 1, negative m times g. And we have
T1y, which is T1 sine of theta.
T1 sine theta. Now, how about this one? What do we know in this equation?
The mass.
We know the mass.
And gravity.
And gravity. And we know sine theta. Can we solve for T1 in this one? We can.
Yes.
So all we need is the y direction to solve this problem. Turns out we don't care what T2 is because it didn't ask us, right? So we're good to go.
Oh, okay.
You can just solve this equation and you're done. Not a very good circle.
Yeah, but I understood that way better. Awesome.
It seems very complicated, but once you understand how to split the vectors into x and y directions and then split the math into x and y directions, you'll find something that's pretty easy to solve.
Yeah, I get kind of confused. I'm not used to seeing like this is equal to this is equal to this, like so many things.
You'll get used to it.
Similar.
You'll get used to it because we'll do it again and again and again.
So I'm gonna do those over again and we'll see how it goes. I think I'll be able to get it now. So
Okay.
if I plug numbers in. Thank you for staying.
You're welcome. You have a good one.
You too.
See you later.
See ya.